So that's the video. And that's the general definition. Obviously, we want to quickly move into some explicit examples that will help us understand what's going on. But the first thing we should see is that there's actually a local model for this type of map, and it is this. X and M. I is modeled by the map Bn minus 2 cross D2 maps Bn minus 2. I guess these are n manifolds now. And this map is such that we just have this y on the disk dimension, on the disk factor, where m sub x is just some natural length. And so the picture of this, which you may have seen before, something like
Just for x is in the singular set.
actually, if you allow this to be 1, then it's everywhere.
Oh, yeah.
Yeah, but good point. Good point. Not today, Joseph. If I can get this to look anywhere close to good. Problem is you start erasing to make it look a little better, and then it just looks smudgy. Something like this. Colors should help. So let's see. So, the point is actually, maybe a little too fat. This needs to actually come down into here, and this actually needs to sort of come up. I'm just going to give the opportunity for one more time. I think I want it to be skinny. I don't know if that's any better. So this is our point X at the middle, and the map then is down to this. So this is just the D2 dimension, but it's this picture crossed with the ball. Other appropriate dimensions. This is X, and then sort of the thing to think about is that this edge here gets identified with this edge here. And we can track the nearby points. So if we take some point here, I'm going to call this, I'm going to call it Y for now. It has 3 limbs in this picture. So in this picture, M sub X is 3. Okay. And then maybe the observation is that M sub X, this value is locally constant. So it is constant on connected components of S pi. Let us say the other side. Okay. All right, so there's another, so here's another sort of example of what this might look like. I guess this is just a very simple example of a branch covering of the disk. Or yeah, I guess maybe this isn't a standalone example, but it is sort of a picture of what can happen locally. Suppose we have some disk down here, and now I'm calling this Y. We have this point Y here. Let's think about this little arc that emanates. Here's a picture of a, did I give D a name yet? Where did D come from? D will show up as. So D is going to be the degree of the cover. This will be an example of the degree 3 cover. And what's going on here is that our branch point Y is actually lifting to 2 branch points, Y1 and Y2, such that in this local picture, it's a 2-to-1 cover, and in this local picture, it's a 1-to-1 cover. Okay, so M of Y1, or these should be X's probably. X2, X1. M of X1 is 1, while M of X2 is 2. And so this is an example of something that can happen when you have irregular covers, which is that the pre-image of your point from the branch locus can have multiple pre-images that, and their local degrees can be different. So this MX is called the local degree. And so what we actually see is that the inverse of the branch locus decomposes as the singular locus union star, union some other bits, where this is called the pseudo singular. Okay. So the pseudo singular set consists precisely of those points which map into the branch set, but whose local degree is 1. But let's not. We'll get. Let's just go. Any questions? Okay. So what do we see? Well, for a regular value y in n, we say that the count of the size of the pre-image of y is called the degree. Is the degree of the branch covering. So for example, let's throw in a regular value in this picture. We would actually get to see what would that come up with. Maybe here, here, and here or something. Have 3 lips. And the other thing we see is that for singular values y in the branch locus, we have that the sum of the over the points in the pre-image of the local degrees is always d. Okay, so for example, in this 2 and 1, add together to get 3. And I guess this follows from choosing a regular value close to y and seeing what has to happen close to the pre-image. Kind of like we see in that picture. Okay. So the last thing I'll mention about the general setup before moving on to some explicit examples, and then at first restricting our attention to surfaces, is that there's a whole other story here along the lines of this. So the branch covering pi from m to n determines a representation rho sub pi from pi 1 of n minus a neighborhood of the branch locus onto the symmetric group of order d. Permutation, or not the permutation group on d letters of order d factorial, called the monodromy. And then the connection here is that the pair m pi is determined the triple n b sub pi and rho. So the data of the covering map can be completely encoded by, in the downstairs picture, where you have the ambient manifold, the codimension 2 embedding, and this representation into some symmetric group, which has to have certain properties, right? So it's going to take meridians of the branch locus to elements in the symmetric group, and they have to satisfy some relations. I guess that's coming from the fact that it's a representation. And this side of the picture, including the justification of this fact, is something that Daniele spells out really nicely, and I've put into the notes as well. But I'm not going to really talk more about that for now. But sort of in the back of your mind, you should be thinking about representations of the non-complement, or the not in codimension to embed complement onto some finite group. That's what's giving the covering. So, common examples are going to be when, I guess maybe this is not quite a surjection, because it's actually just, it's surjecting some finite subgrouping. So common examples might be, for example, a cyclic group of order P. That's where the notion of a cyclic branch covering comes from, which is probably the most familiar to people these days. But you also have these dihedral branch coverings, which come from a surjection onto a dihedral group. That's where this picture sort of comes from. This is the local picture for a dihedral threefold covering.
When you say n pi is determined, do you mean like diffeomorphism that respects the cover?
Yeah, probably like yeah, exactly. A diffeomorphism that commutes with the commutes, maybe not quite the right word, but commutes to the square commutes, or the triangle maybe in this case. Yeah, exactly. Okay, so that's what branch coverings are, and this is a very rich area of study. Even just studying branch coverings of surfaces, like Phil talked about, Phil Engel talked about earlier this semester. Even there are these open conjectures about when you can have a branch covering between of certain types between certain surfaces and so on. All right. Okay, so what I want to just do now is just give a couple of examples of branch coverings of surfaces that are going to be sort of useful for us. So one of the most common examples that we'll encounter, and I'll sort of just describe this very graphically, is if we take a genus G surface and we consider the map, which is the hyperelliptic involution map, which is rotation by, I'm going to write pi, but we've already got enough pi, so let's write 180 degrees. Rotation by 180 degrees, you have this quotient map, and this descends. If you think about what the image under this quotient map is, it's something that looks like this. You're like, oh, bump there, bump, bump, bump. Kind of like a lobster claw sort of thing. This curve gets taken onto this curve, and maybe that's its image. Same thing here. Here. And the branch points descend thusly. And what we see is this is a d equals 2, so this is the covering pi. This is a degree 2 covering, and it's cyclic. Yeah, I guess I didn't really say what I mean by cyclic, but based on what I said over there, it has something to do with where does the representation send a meridian at each of the branch points? Well, it's going to send it to the non-trivial element Z-mod 2. And that's what's going to determine this branch covering. So what we see is that we have a map pi from sigma G to the 2 sphere, where the size of, and it's twofold, it's 2-to-1 branch covering, And the size of the branch locus is going to be, I guess this maybe going to be 2g plus 2. Is that right? Works in this example. All right, so that's one example. Let's draw another picture. Maybe I'll try to fit it right here. Okay, so this is supposed to be a very long pillowcase, like maybe a king pillow. And let me for this one, let me start instead with the base space down here, which is also going to be the pillowcase. And here what we want to do is we want to take we're going to branch the two-sphere along 4 points. In this example, the order of the branch locus, or the size of the branch locus is 4. And to build this cover, what we're going to do is we're going to cut open along arcs connecting the branch points. The way I've colored these branch points, maybe I'll just write this once, it's meant to indicate that the monodromy representation is sending the meridian of these points to the same element in the symmetric group. And in this case, we're mapping into the symmetric group on 3 letters, and I'm sending these points to the transposition of this sort, and these points to the transposition of this sort. But what we can do is we can sort of cut this open along these arcs and glue some number of copies of them together. In this case, we'll glue 3 copies together. So let's do it like this. So if I draw these arcs back in, you'll be able to see where I did my gluing after I cut. Oops, I switched colors. What happened? Okay, I can fix it. And so what we see upstairs is 3 copies of the sort of cut open pillowcase glued together along these cut arcs. And what's sort of interesting about this is each of the branch points lifts to 2 branch points, exactly like in that picture there, right? Where this one is actually, so the multiplicity here is 1, and the multiplicity here is 2, and same for course many guys. So anyway, words are, this is the cyclic guy or the hyperelliptic covering, and this is a picture of a dihedral threefold branch covering. So what's kind of cool about this example is it's a covering of the sphere to itself. And so you can just kind of think, well, we like putting our manifolds in a good position with respect to a sphere. So if we're taking a branch covering of this type, then that sphere is going to lift to a nice sphere upstairs. And so that might tell us something about the decomposition we get when we left. So that's a little foreshadowing. Okay. Any sort of questions about these examples? So like I said, there's sort of a very rich, so it's not 7 seconds, it's 57 seconds, or 9 seconds. So I was like, not even a second. There's a sort of a rich way to take this labeling information, where you just say where the meridian of each connected component or branch locus goes on the representation, and build this cover upstairs. That would maybe that's something we can sit down and talk about sometime next semester. Any questions? Now I'm suddenly paranoid not spell this right. Hurwitz? It doesn't have a C in it, does it? Yeah, it does. CZ?
Instead of T.
like that. You know, I knew. So we have this nice formula that tells us how the Euler characteristic changes over the time. That's useful to keep in mind because, well, it lets you keep track of the complexity of this, the sort of surface pieces in your branch covering. So let's suppose that pi from, let's say, f tilde to f is a d-fold branch covering of surfaces. Then what we have is that the Euler characteristic of the cover is equal to e times the Euler characteristic of the base minus the sum over points in the singular set of the local degree minus 1. And just notice if x, well actually, okay, so just notice we could actually define this to be the sum of like points in the surface because anything not in the singular set has local degree 1, so it won't contribute to the sum. So that's kind of fun. Okay, so for example, maybe as an exercise you can check this. Well, maybe the first exercise is to prove this, which is not too bad. And then the second exercise is maybe the first exercise. Check this for the previous two examples. Or maybe even other examples that you might want to look up. Okay. So, well, one observation. Here are some observations. We're just rolling through things here. So let's consider the case that the base is a disk. If the base is a disk, so actually you can kind of see this here. You could think of just maybe puncturing these base spheres, right? Or maybe you could think of this one. You could think of cutting it in half along this curve. Right? This is really sort of two branch coverings over the disk glued together along the boundary where they're compatible. So we're actually seeing the lift of the branch covers up here. But the point is that if f is a disk, then f tilde is a compact surface with non-empty boundary. So there's nothing too deep about that statement. That's just basically just the statement that the map is proper. But it has some nice consequences for us. So the second consequence is we can take this covering and we can cross it with I. So we can let BT be our, so we have a disk with some marked points, right? And we can cross this thing with I. So what we see is that then what we see is that f, pi from f to d gives rise to, maybe I'll write it as pi sub I. I don't know what you think, right? But I'm going to do it. Pi sub I from b tilde to b, where we just take the covering and we just cross it with I. And the covering, you can see. So in this case, the covering space, b tilde, is equal to f tilde cross I. Sorry, this is f tilde. F tilde cross I, which is just a handle body, some genus G handle body. So, and then actually, let me just make one more remark, and I'll just say similarly, we get a map, maybe I'll call this one pi sub d2 from z tilde to z. I guess I should define what z is, where z is, or z comma d is equal to our marked disk cross d2. And actually, and so on, right? We can cross this branch covering. We can thicken this branch covering to any sort of dimensional thing as long as we thicken our codimension 2 submanifold to a corresponding one. And so in this case, we have that z tilde. So z is just a four-ball. So we have the z tilde is a four-dimensional one-handed line. There's something I'll call zk, which is, I guess, what we haven't really talked about, but we've talked about boundary connected sum, so you can take boundary connection sum of a bunch of copies of a ball across the circle. This is also a four-dimensional thickening of a wedge of circles in Euclidean space. Anyway, more of that come someday. So then the proposition that's staring us in the face is that any branch cover of a trivial tangle is a handle body. And two, any branch cover of a trivial disk tangle is a four-dimensional one-handle body. So what we see is that our pieces of our bridge splittings and our bridge sections will lift nicely under branch coverings to give pieces of Haggard splittings and trisections. So this is the sense, I'm getting a little ahead of myself, but this is the sense in which the theory of trisections and bridge trisections is so, and bridge splittings and Haggard splittings so nicely behave with respect to branch coverings. All right, so I think what I want to do now is to give an example of this that I hope can illustrate sort of how to do this in practice. Okay. And I'll do it in this sort of elliptic hyperelliptic case. Okay, so the example here, I guess, is obtaining a Haggard diagram for M from a shadow diagram of, I guess, n b pi, where in this case M is going to be some 3-manifold and n b pi is going to be S3 link inversion position. Okay. I guess I'll start off here and see how my space holds up. Okay, so let's start off with our number 3. Okay, so here we have a 2-bridge splitting of the Trefoil, and one way we know how to represent this is to draw it as a shadow diagram, where the red shadows sort of look like that, and maybe I'll get 2 colors for the blue shadows, just to keep them distinguished. Not green though, maybe. Okay. And so what we want to do is we want to take this sphere and we want to arrange it so that we can sort of naturally identify it as the quotient of this hyperelliptic involution. And so to do that, we're going to draw it like this. So first of all, I'm going to close this up, and then I'm going to make it have some curvature. So this, maybe just for at risk of making things look bad, this line is actually this equator right here. And my bridge points are going to look like this. So my red arcs look like that, and now the blue arcs are going to be a little bit tricky to draw, but not too bad. So one thing I've kind of done is I've pushed the back of this surface down and below, and I've pushed the front of the surface in front and below. And so when I cross over into this region of the sphere, I'm actually going to be on the back of this sphere. So this blue arc, which leaves this point on the front, but then it passes into the back realm before coming over here, passing over the front end and there. So if you puncture your balloon here and open it up, it'll look like that. Now so now this is a key point. The purple curve is determined in the exterior of the blue curve because, and actually the same was true of the red arcs. Once I drew this red arc here, there's actually a unique way to put this red arc in between these points up to jumps over the first arc, because this arc connects these two dots. So if I think about, I have to avoid it with this arc, which means I'm avoiding a disk. So I'm drawing an arc on a sphere that avoids a disk. So I'm just drawing an arc on a disk. So there's really a unique way to draw the second arc. And this is a general fact, which is that, I don't know if I said this earlier, only B-1 shadow arcs are required to determine the bridge splitting. That last shadow arc will be determined. So if I wanted, I could not draw the purple curve, but I think I actually will draw it. So it starts off here, say, and it leaves along the back of this surface. And it comes into the front momentarily, and then it finishes its life back until it arrives there. Okay, so this is just a translation of the picture. Okay, and then the last thing we're going to do then is we're going to think about how is the cover obtained from the base. Well, one way to think about it is we connect the points with arcs, and we can do this because this is going to be a cyclic cover, and all of the meridians are getting mapped to the same thing under the monodromy representation. So we're actually allowed to just cut this open and lift it. Cut this open and then take two copies of this sort of cut open sphere and glue them together in the way prescribed by the cutter. So that's similar to what was done here. I cut open here, and I glued three copies together in a way that was prescribed by my monodromy. So in this example, what that's going to look like is I'm going to cut open along our and the result is going to be something that looks like this. So this is now an annulus, and in general, it will be a punctured sphere. If I had more bridge points, it would be a higher punctured sphere, and this cuts our shadow arcs up into bits. So maybe I'm going to draw the red as not coinciding with the yellow, although the astute student will notice that the red and the yellow marks are actually the same mark. But the point I want to emphasize is you don't have to do this cut along the shadows of one of your systems. A priori, I could have a complicated red tangle and a complicated blue tangle and a complicated green tangle, and I don't cut open along any of them. Okay, so these guys get cut, goes like that, and this goes, you can see through there now. This goes down here, and then it goes here, and similarly for purple. And because I want to construct a twofold covering, or actually maybe I want to construct some other sort of covering. This is sort of the beginning steps no matter what, although different coverings are a little bit harder to draw. The one I want to construct is the twofold, necessarily cyclic branch covering. And so what I need two copies now of this sort of fundamental domain of my covering. So let's, oh, I guess I'm going to have to. I can't copy paste it in class, so. I'm just going to have to draw it over and over again. Okay, so. So take my two copies. And so the bottom one I'm going to draw looking like the other one. And now for the top one, I want to think about what does my action do? Well, my action interchanges these with a rotation. And so red arcs that are sort of equivariant with respect to this action are on the back of the surface like that. And then what does blue look like? This. And so on this one, this goes on the back. Things like that. And similarly, purple starts off on the back here, and before going up the front, returning to the back, and it does the opposite here. Front, back, front. Okay, and actually, you can start to see why I maybe am regretting my choice to include the purple arc when I didn't have to, because although it's sort of like a nice sanity check that you did it right. Anyway, so then we glue these together, and of course we're going to get a torus. And you might have expected that we were going to get a torus from, say, this example or the Riemann-Hurwitz formula or whatever you were following along with. Our cut arcs lift to these curves here. Our red curves lift to a pair of curves, which not surprisingly are sort of parallel there. And we see even for the third time why we really didn't need the second curve, because it ends up being redundant in this picture. And in a general picture, you can see on a genus 3 surface, we would lift 1, 2, 3, 4 shadows and get 4 compressing disks, but they'll separate, so one of them is redundant. So we can always just sort of forget about one in general. So we're not going to do that quite yet. So now this is a little bit easier to do. There's the blue curve, lifts to that simple closed curve. And the purple one lifts to this simple closed curve. Something like that. For the fourth time, I'm regretting getting so many curves. So I'll just finish by getting rid of the extra ones. And also isotoping the blue curve around a little bit. To get that picture. Okay, it's a worthwhile exercise to check the blue curve is actually isotoped. It's very symmetric here. In fact, when you lift these things, the result you get is equivariant with respect to this involution. Whereas maybe the more usual diagram we might like blend space L31 is not necessarily. And also maybe just remember that one way to think of the Treflo was as the rational link K31. And now we've lifted to get the blend space L31. And that's not the coincidence.
What did you just say? L31 doesn't have any two-fold symmetry?
No. The diagram I drew there at the end is not obviously equivariant under the obvious involution. You have to kind of you need to bring this point around, and because if I involuted this, I'd have all these. We like to draw our curves so that they're on top of the surface as much as possible. But the equivariant ones should be sort of half and half. That's all. Okay, so just about out of time. I just about said what the necessary things to say. So let me put this on the board just since it's exactly what we were just talking about. So there's a theorem of Haskell-Susskind. And the result is that every simple closed curve on a genus 2 surface is isotopic to a curve that is preserved by the hyperelliptic involution. So it's possible that I've just said enough right here to convince you that any curve on a torus, which is a slope, a PQ curve, or an MN curve, can be arranged to be invariant under the hyperelliptic involution. It turns out the same is true for the genus 2 surface. And so, for example, what might a curve look like? Well, it's probably going to look something like this, maybe. Something like that. That's an example of a curve that's coming. So this uses the hyperbolic geometry of the surface, and the fact that we can find. In fact, you can find a geodesic curve that's preserved by this option. But anyway, one corollary that's important for us then is that since any curve can be done this way, actually any collection of curves can be done this way. So in fact, any Hagar diagram on a genus 2 surface, or any trisection diagram on a genus 2 surface, is made equivariant with respect to the hyperelliptic involution. So the corollary I'll state for now is that every genus 2 Hagar splitting is a twofold branch cover of a 3-bridge splitting. And maybe what I should have stated before I said that is that if L admits a B-bridge splitting, then I was going to say it like this. Cyclic p-fold branched cover M sub p of L admits a genus p minus 1. Oh, why did I switch to p? Come on. D. Sorry, guys. Excuse me. P minus 1 genus Hagar split. So in the case of twofold, it's a B minus 1 Hagar split. And this is, it doesn't have to be cyclic. Like we remarked earlier, any branch covering of a bridge splitting lifts to a Hagar split. But the genus is going to change in a complicated way if it's a complicated branch covering. Okay, what I had left was a bunch of facts about branch coverings of knots that, it's just, it's such a cool part of three-manifold topology. But I think we'll have to table it for now. So that's actually pretty good. I'm pretty happy. Next time we can talk about vein surgery. And then next week we'll do four manifolds. Any questions? But if anyone's interested, we should definitely talk more about branch coverings, because it's a pretty interesting thing to think about, especially from a theory of trisections point of view.
So the reason why this is so successful is because